Welcome back, Lecture 41. We will hopefully finish up Newton's method today. One of the problems that I want to make sure we look at is a problem in WebAssign that, as I glanced through WebAssign, was the one that kind of caught my eye as the most difficult one in the list. So let's see if we can make a good diagram and then actually get a couple of approaches to that problem. I like the problem because it has a lot of things that we've done this semester all rolled into that one problem, and that's probably the reason why you won't like the problem. But I like problems that connect a lot of stuff that we've done, and that problem connects a lot of stuff that we've done so far in this course. Any burning question or issue before we go back into the middle of a problem that we
Will you start at the very beginning of that problem? Because I don't know how you did what you've already done.
Okay. Let's make a quick review of kind of what we're doing. This diagram's a little cluttered. We used it yesterday. But we're searching for the root of a polynomial. We're searching for this point. We have a guess. Sometimes we're given that guess. Sometimes we come up with that guess on our own. Sometimes we come up with a guess like in the technician. We'd be reading the technician, and we'd come up with a guess. Like, I don't know that you'd ever find like a good logical guess in the technician, but occasionally you might find like a first value in the technician. Hey, it worked. So we have a first guess, x1. Doesn't look like a very good guess because it's a long way from where r actually is. So what do? We go up to the curve. There's the point. X value is our guess. The f of that x value, we draw a tangent to the curve. It comes down. And if this is set up correctly, we went over some ways that it could fail, then it should be better than our original guess, which in this case it is. Then we do that process all over again. Come up to the curve, draw the tangent line. Now we're even better. Come up to the curve, draw the tangent line. So we end up with this iterative process. As it turns out, each time you iterate the process, you get, again, if it's going to work, your new and better approximation at the root. You can take the old one minus this fraction, the function at the old one, over the derivative at the old one. So you're basically using the prior answer to generate a new answer. So, and you can do this process as long as you need to for the conditions in the problem. So there's Newton's method, or Newton-Raphson method. The example that we had started right at the end of class, this is what is asked of you. What is the cube root of 4? So how can we find, using Newton's method, the cube root of 4? Well, Newton's method is only good if we have a function and the derivative of that function that we can actually plug numbers into. So we need a function for which this is the solution. Okay? So we're not given that. So you have to kind of make your own. So what would the cube root of 4 be a solution to? What?
X cubed minus 4.
Okay. So if we had x cubed minus 4, then the cube root of 4 is a solution to that. So you kind of say, well, I'm working with a cube root. I better have something cubed in the equation. So when I solve that x cubed for x, I get a cube root. And then we basically have to make 4 the solution to it. So x cubed minus 4. Casey, is that your question? So this is what you're handed, and then you have to build the equation. I think there's a WebAssign question. We'll finish this. But there's a WebAssign question. Find the square root of 1,000. Am I remembering the right question? Something like that. Anyway, well, if that's what we're looking for and we're going to use Newton's method, what is the equation for which this is the root?
1,000 equals x.
Would be
X squared minus
x squared minus 1,000, right? So depending on what you're given that you're searching for, you can build an equation that has that for its solution. I think this is a web assign.
Do you like have to work backwards on it?
Yeah, kind of. I mean, we all know that we could find this very readily by punching a couple buttons on our calculator. But this is a section in the book where we're using first derivative for a variety of things. This is one of the uses of first derivative where we don't have to necessarily depend on our square root capability of our calculator or our cube root capability of a calculator or a 7th root or an 11th root, whatever. We can use calculus and basically use a 4-function calculator, add, subtract, multiply, and divide, and we can find something like the square root of 1,000 or the cube root of 4 just by adding, subtracting, multiplying, dividing. All right, there's our function. I think yesterday we also, right as class ended, we got the derivative of that function, which is 3x squared, and now we're in business. I don't know if we found an initial value that we wanted to start with. I think we were just about at that point where we said 1 was too small, right? And 2 was too large, so the actual root of this equation is somewhere between 1 and 2. So we said 3 halves. Okay, so we did get to that point. All right. So we're going to make a guess. Hopefully it's reasonably close. I don't know, what is 3 halves cubed? It'd be 27/8, right? What is that? What is 27 divided by 8? I like that. You're thinking this morning. He said a number. It's good. As opposed to like, socks or a towel or something. It'd be a number, right? It's good. I like that. What is 27 divided by 8?
3.375.
Okay, so it's reasonable. So we'll start with 3 halves. How do we get x2? x1. We'll go ahead and write it all out this time since it's the first problem today. Minus f of x1. Have this memorized on Friday for the test over f prime of x1. So x1 is 3 halves. The f of x1 is that. Put it into the function over the derivative at x1. So this is what I mean by just a 4-function calculator. A little calculator you could buy for $1.50 can actually find the cube root of 4 even though it doesn't have the capability of doing cube roots. So we're going to add, subtract, multiply, and divide. So what do we get up here? What did we say that was? 27 over 8, which was 3.375. So 3 3/8 over, what do we get here? 9/27. Is that right? So at some point in time, we're going to have to abandon exact numbers, probably, because it's just going to get a little too cumbersome. But this isn't awful. What's 27 over 8 minus 4? Negative 5. Okay, negative 5/8. Because this would be 32. I'm sorry, 27/8 minus 32/8. So it'd be negative 5/8. And down here we've got 27/4. So 3 halves. We're going to have a minus a negative. So we're going to be adding on. Now, is that what we decided? We didn't have enough. 3 halves was not large enough for the cube root of 4, right? So it kind of makes sense that we ought to be adding something on to this, and we're going to add on 5/8 divided by 27/4, so we're times 4 27ths. So 5 over 54. Probably abandon exact values at this point and go to decimal approximations. What is that? One point, give me about 4 decimal places. 5925. Anybody else get same? Okay. So we knew 1.5 wasn't large enough. Just take that decimal and cube it and see what you get. Are we getting close to this value being cubed equals 4? 4.039, so that's pretty good already. If we did one more iteration, let's start it, okay, just to see what the arithmetic would look like. So if we wanted to get a little bit better, that's pretty good already. We would want x2, there's our approximation, minus the f of x2 over the f prime of x2 Now, some of you that kind of want to explore the ins and outs of your calculator, you can actually program your calculator to do Newton's method. So basically, you tell it what iteration you want, and it can basically take the answer, plug it in as the data, compute it again. So anything that has a loop like this, you can program your calculator with probably, I don't know, 5 or 6 lines of code to actually do this for you. Nicole?
We're trying to figure out how we got the 3/2 again in this first step that we plugged through.
We made a guess about the cube root of 4. We said that 1 cubed was 1 and 2 cubed was 8. So we're really looking for something that we can cube and get a number somewhere between 1 and 8. So we figured it had to be a number between 1 and 2. So somebody suggested 1.5.
So if it gives you like an interval, would you pick a number in between that interval that when you plug into the equation, it'll give you a y value that's also in the interval?
Yes. So, and I think WebAssign does that.
Yeah,
It
that's
gives you
perfect.
an interval. What I would do when it gives you an interval is, let's say it gives you an interval from A to B, I would go ahead and put A into the function and see what you get, and put B into the function, see what you get, and then kind of make a guess. We're looking for, in this case, 4 looks like it's pretty close to the middle, right?
Right.
Of 1 and 8. If we were looking for the cube root of 2, instead of picking 1.5, maybe we would pick, 1. You can pick either endpoint and probably accomplish the same thing, but this gets us to an answer a little bit more quickly.
Okay.
So you just pick the one, either endpoint that seems appropriate or some value in between.
So would I pick this number here to plug in?
All right, everybody convinced that this is going to get us the next best guess, so to speak, at the root of this function?
Do you ever get the exact answer?
Okay. Yes, thank you. That was 3x squared. Thanks. Will you ever get the exact value? No. But you'll get as many decimal places of accuracy as you want, depending on how many iterations you do. So if, for example, I don't know, did anybody run that through?
Yeah,
Did you run it through?
1.5874.
5874? Okay. Now, we expected it to be a little less, didn't we? Because we cubed that and we got something larger than 4. So we need to back off of that. That's just a little bit too large, so this seems to be. So at this point in this problem, 1 certainly is good. We're not going to change, as we could do this 10 times. It's not going to change the 1. Do you think the 5 is also good? And it may be, in fact, that the 8 is also good. Now, what do I mean by good? Meaning if we try further and further iterations, there's a good possibility that the 1 and the 5 and the 8 are not going to change if we did this problem 100 times. So you can keep going and get as close to this as you want to, based on decimals that kind of refuse to change beyond that point in time. somebody cube that real quickly, and what do you get? 3.998 or something? 999?
9999992.
Okay, so that's pretty good. So we've done x3.
Yeah.
You've got what?
I cubed the entire decimal.
Oh,
and got
without
4.
truncating the decimal?
Yeah.
And you got slightly larger than?
Right
Okay.
over 4.
Okay. But when you truncate those decimals, you lose that, and so when you cube it, it becomes a little less. So we're getting pretty close. And that is as far as I would ask you to go on a test. Okay? Possibly have you find x1 and then go to x3. Questions? Yeah, Nicole.
When I asked you about the interval one before, do you think that you could help us find that value? We really can't figure it out.
The starting value?
Yeah.
Or okay.
Yeah.
So tell me what the problem
The
itself
problem is x to the 4th plus x minus 4 equals 0.
says. Okay, so
And
there's your
then
function.
The interval is 1, 2.
1 to 2?
Yeah.
So when you put 1 in there, what do you get? 1 plus 1,
We got
negative 2. And the f of 2 is 16, 18, 14?
Yep.
Okay. So is 0 somewhere between negative 2 and 14? Yeah. So we know by the intermediate value theorem that there's a root somewhere between 1 and 2. So if you had to make a guess, is it closer to 1 or closer to 2 based on what the f of 1 and the f of 2 are, which would you say?
Closer to 1.
Closer to 1. So you can start with 1 if you want to.
Could we have picked like 5?
Yeah, but it would
Well,
have-
that's not between 1 and 2.
Oh.
Unless they changed the rules. Did they change the rules overnight? They may have, and I didn't get the memo. Okay? But if they didn't change the rules, then 1 and 2, we've got to pick a value. If you don't think 1's good enough because it's negative 2, then you might want to pick 1 at, or x1 at 1.2 or 1.3. I don't know, but if I'm going to choose 1 or 2, I would certainly choose 1 because 14 is very different from 0. Negative 2 is a little different from 0, but not that far away.
So when you said 0, you meant 0 as a y value, but we still have to figure out what the x value
That's
is.
exactly
Oh,
right.
Okay.
So 0 is we want the f of x to be 0, the y value to be 0. We're searching for the x value on our first guess that causes that to happen. So I think 1 is legit, to be honest with you, so that I can, for some consistency and uniformity, when I give a test question, I'm probably going to give you x1 because I want everybody's first iteration to be the same, second iteration to be the same, and so on. But if you're searching, you can just usually can get away with picking 1 or 2, but I would start with the one that seems a little closer to the answer. You okay from that point? Okay, everybody okay from that point on this web-assigned question?
I guess.
Sorry for being a smart aleck. Some days I just can't help myself.
It's okay, I can handle it.
Anybody else from WebAssign? All right, this doesn't look like a Newton's method problem, but let's see if we can solve it. And I think there's a WebAssign question similar to this. We want to know where these two things are equal to each other. What is the Newton's method problem related to finding where these two functions are equal to each other? If they're equal, then what is 0? Because that's what Newton's method is good for, to find when something is 0. If these two are equal to each other,
Do they intersect each other?
okay, keep going with that thought. They intersect each other. And if they intersect each other, isn't their difference equal to 0?
Yeah.
Right? So there's the function that we would want to find. So if you're looking for where two things are equal, Newton's method works for that. just in whichever order you want to, subtract them, and if they're equal, their difference would be 0. So that's what Newton's method is good for, finding the root of some function.
So you wouldn't have to do the derivative thing?
Oh, yeah. That just gets us started. Okay? That's our function. I'll tell you what might come in handy here is a graphing calculator, and graph that, and graph that, and see kind of approximately where they intersect, and that could be our starting value. So the derivative is going to be part of the Newton's method iterative process. Natural log of something, what's the derivative? 1 over that times the derivative of that, which is,
Minus 1.
and then derivative of x, I can handle that one. That one would be 1. Making progress. This probably wouldn't be that bad to guess at, to be honest with you, especially if you don't have a graphing calculator handy. If x is 1, that might be pretty good, actually. 4 minus 1 squared, that's 3. Natural log of 3. Remember, I put in x equals 1. Is the natural log of 3 pretty close to 1?
Yeah.
What is the natural log of 3? 1.09, right? Something like that. So you don't need a graphing calculator necessarily. I just kind of did trial and error. In fact, the first value I put in seemed to work. So I would pick x1 at 1. So if we wanted x2, it would be x1, which is 1, minus the function. Now, this is our function. Trying to find where two things are equal, so their difference is 0. So the difference is the function. All over the derivative. And there's a lot of computation. I don't know that there's anything gained by getting a common denominator here. I mean, it might look a little better, but you're probably going to be using the 4 function keys on your calculator anyway to accomplish this. But that ought to indicate to us how good our initial guess was. So somebody said that was about 0.09, right? The numerator.
0.0986.
And is this denominator negative? It's negative. So we're going to be subtracting a negative, right? So we're going to be adding on. So it's going to be 1.059. And you know what to do from there. That becomes the data for the next round. Anybody that ran that through your calculator and got something different, and you have a question about that? All right, the WebAssign question that I wanted us to look at is actually question number 28 in the textbook. I don't think anybody actually had your WebAssign printed out, right?
No, but I can bring it up.
So this is page 326, and it is problem 28. And I don't think anything is randomized in the WebAssign. I think this will be the exact same problem for everybody. So I think a diagram helps a lot, and I think this ties together a lot of things that we've done recently. Let me read it. Should I read it out loud?
Yeah.
Okay, so I'll read it out loud. Of the infinitely many lines that are tangent to a curve, the curve is given, y equals negative sine of x. So there are lots of lines that are tangent to that curve and also pass through the origin. There is one that has the largest slope. So we're going to try to maximize the slope. Use Newton's method to find the slope of that line correct to 6 decimal places. Okay? I don't know that we'll get in class correct to 6 decimal places, but let's start the process. We could probably get 2 or 3 decimal places in class. All right, so the function is negative sine of x. So negative sine of x starts with the negative branch first. And there's more to it, so I'm going to probably clutter this diagram too much, but let's make sure we're kind of choosing the right piece of the diagram to make our decision. And so on. I guess we could look at more of it over here also. So I'll read it again, since you're not looking at the problem. Of the infinitely many lines that are tangent to the curve and also pass through the origin, there is one that has largest slope. Well, think about ones that are, if I wanted to make this tangent, I could come through the origin, come out here. That's tangent. Now, what am I trying to maximize? The slope. Can I do better than that one?
Yes.
Yeah. And in fact, I could do a lot of others out here that are smaller than that, right? That as they come out from here, they could be tangent to the next peak of the sine graph. But this one right here appears to maximize the slope. Does that seem logical?
And we're still looking for the one that goes through the origin, right?
Right. So we know it goes through the origin. And then we want it to be tangent to this curve. And we want the largest slope possible. So the peak of this graph, which probably, if my diagram is at all correct, I think we're going to be tangent before we reach the peak of that, right? And the peak would be at 3 pi over 2?
Yep.
So if this picture is reasonably accurate, it looks like our value the point of tangency, anyway, is somewhere in that interval. Pi, we're going to get numerical answers here. So pi is 3.14, and 3 pi over 2, another 1.57 added to that, so 4.71, is that right? So our value is somewhere in there, the point of tangency. Now let's make a reasonably intelligent guess. Which do you think it's closer to?
3 pi over
3 pi over 2. Yeah.
Looks like it's closer to 3 pi over 2. 3 pi over 2 is right here, and pi is way over here. So it looks like we're a whole lot closer, if my diagram's accurate, and I think it's accurate enough, that we're going to pick a value that's closer to 4.71. We don't want to pick 4.71, by the way.
4.70. No?
What would be wrong with
Six.
4.71?
It would be.
It'd be flat.
zero.
The derivative
Yeah.
would be 0, and then we'd be dividing by 0, right?
Mhm.
In the Newton's method. So we certainly don't want to pick 4.71. Somebody said 4.5.
Yeah.
Okay.
Okay.
That actually sounded pretty good. Now, we don't know what we're putting 4.5 into yet, but we're established as far as where we're going to start.
Why aren't you putting into the sign, the negative sign? No.
Why aren't we?
Why aren't we using negative sign of that?
Okay, we are now. Oh, well, that's not. We don't want to maximize the value on this curve. In fact, we know what maximizes the value on this curve.
And tangent line.
1 is the maximum you're ever going to get. We want to maximize the slope of the tangent. So we need to figure out the slope of the tangent. Now, you said one way is we can use the function, and we know that the slope of the tangent is the first derivative of the function. And what's the derivative of negative sine of x?
Negative cosine of x.
Negative cosine of x. Now, we also have a second way of finding the slope of this line.
Points.
We have a point here, and we also have a point here. What's the nature of the point here if it's a point on this graph? Isn't the x value just some random x value? But if we know the x value, isn't this the y value?
Yes.
So if we have 2 points on that tangent line, can't we find the slope of that tangent line?
Yes.
0, 0. It has to go through the origin, and then it has to go through this point, and that point is any point on this curve, because the y value is always negative sine of x. So another way to get the slope of the tangent is to use the 2 points that we have and difference of the y's over difference of the x's. Difference of the y's, negative sine of x minus 0. Difference of the x's, x minus 0. So we've got 2 seemingly different answers for the slope of the tangent line. Well, if you have 2 things that you know are the same, but they look different, what can you do?
Choose either of
You
them.
can set them equal to each other, right? And kind of solve for that. So that's one way to accomplish this problem. That's not actually the way that I wrote this problem down the first time I solved it. So I took that slope of the tangent, and I know I want to maximize it. How do we, in fact, that's part of what we've learned recently, how do we maximize anything? Or minimize anything?
Set it equal to 0.
Take its derivative
Oh.
and set it equal to 0. So if we want to maximize this, let's take the derivative of this and set it equal to 0. Now, setting it equal to 0, does that ring a bell with Newton's method? We know how to do that. That's what Newton's method is good for, is setting something equal to 0. So here's what I want to maximize. So we'll take the derivative of this function and set the derivative equal to 0. Chandler.
Why can't you use negative cosine x?
Yeah, like that just seems so much easier.
It's easier to use it.
Like all you have to do is just like a one-step kind of thing.
Well, all right, let's try it. What's the derivative of negative cosine of x?
Sine of x.
Okay, and where's the sine of x equal to 0?
1.
Somewhere in here. In fact, I think I tried that. I like that better too. First time I tried this problem. I didn't get anywhere with it. So I tried to take the easier function, which is this, and to take its derivative and set it equal to 0. I didn't get an answer that I knew was in the interval that So I took the derivative of this, and it did get me somewhere. And then there's another way that you can accomplish this too, but that is, I agree, it does look easier, but it doesn't get us a solution. So let's take a function, let's call it the g of x. That's this derivative function, which is the slope of the tangent. Sorry, it's not the derivative, it's the one we found with the 2 points.
Where is it?
And we find g prime of x, which looks kind of bad, but it doesn't end up being that bad. So it's denominator times derivative of numerator. What's derivative of negative sine of x? Minus numerator times derivative of denominator, which is 1, all over denominator squared. So g prime of x, this function that we're trying to maximize, we're trying to maximize g, therefore we're taking g prime and setting it equal to 0. Negative x cosine of x plus sine of x so there's g prime. We want to set it equal to 0. You see why I wanted to run through this problem in class? It's just got a lot of stuff to it as far as estimating where the answer is and then deciding how we want to go about maximizing the slope of the tangent. How do you make any fraction 0? By making the numerator equal to 0. So we want to know where the sine of x minus x cosine of x, I just rearranged it so this subtraction was second instead of first, because we want to know where this numerator is equal to 0. So how do we find where something is equal to 0? Newton's method. So this is our, I don't know, give it a name. We've already used f of x and g of x, so let's call this h of x. There's our function. We're trying to find the root of that function, and we decided earlier that we wanted to try x1 at 4.5. Okay, we're going to come back to this. I want to show you another way real quickly of how you can end up with this same equation. Probably a little bit easier, actually. And it's from the bottom of this page right here. The slope of the tangent based on the derivative was negative cosine of x. The slope of the tangent based on using the 2 points on the curve was this. If you were to set those two equal to each other, and I guess you could just cross multiply negative x cosine of x equals negative sine of x. Put them both on the same side. Sine of x minus x cosine of x equals 0. You end up at exactly the same place. That's a little quicker, actually. That's not the way that I solved it originally, but when I looked at the solution manual to see if my answer was correct, that looked a little cleaner, actually, than what I had done. But you end up with the same. I mean, that's where you end up there. This equation is exactly the same as that equation.
Can you go back to the other sheet? Please?
Can I go back to
The sheet?
this one?
No, the one you just wrote out.
This one? Where I equated those two things?
Yeah.
Then I just cross-multiplied.
Oh.
So that's the slope of the tangent from the derivative. This is from the 2 points. They're equal, cross-multiply, and you end up with the same equation.
I thought we talked about that earlier and you crossed that out.
No, Chandler suggested that instead of taking the derivative of this and then setting it equal to 0, why don't we just take the derivative of this by itself? And I think I originally tried that too because it's the easier of the two equations. It just didn't get me anywhere. All right, so here's our h of x. We now have an x1. Let's get the rest of the problem started, and then you can take it to the level of accuracy. I believe this is the last question
Yes.
in your web assignments. So we want x2, so it must be 4.5 minus the f of 4.5. I guess we don't have this yet, do we? The derivative. We have h of x. We don't have h prime of x. That's going to be a mess. What's derivative of sine?
Cosine.
Cosine.
So, are we not even going to use it after that?
And this is a product rule, right? First times derivative of second. Derivative of cosine is negative sine plus second times derivative of first. All right, so let's see if we can write that a little bit larger over here. H prime of x looks like it is cosine of x minus cosine of x. Those drop out.
Yes.
And then we've got minus this negative, so it looks like what? X sine of x? So there's our h prime, there's our h. So we've already got h in the numerator, we need h prime. Now I know that looks awkward, we don't do a lot of that. Sine of 4.5, what's that mean? 4.5 radians, right? So make sure your calculator's working in radians. So there's a sine of 4.5 radians, cosine of 4.5 radians, and so on. I don't think we're too far off, actually, with 4.5 as our starting point. I think it's a little bit larger than that. 4 point. Anybody run it through? 4.59? I don't remember the rest of the decimal places.
So once you get the slope of the tangent line, you're not even going to use f of x. You just need to use that to find.
That's right. That becomes a new function. We're trying to maximize
And that's what we're trying to find.
that function, g. So we took derivative of g, set it equal to 0, and then that's when Newton's method comes in. The derivative of g, here's g prime. We're setting the whole derivative equal to 0. It's a fraction. You make a fraction 0 by making its numerator 0.
Right.
So there's the function that we're trying to find out where it's 0.
And then we don't even use f of x
That's correct.
anymore. After we've
After,
already done
well,
all that.
we are when we finish the problem and we go back into, because we want to know what the maximum slope is.
I got 4.493.
I got 4.50659.
50659. Anybody else get?
I kept the whole. I got 4.49.
Where most of you are getting underneath,
Yeah,
a little bit underneath.
4.493.
Maybe that's what I was thinking of. 4.59. Maybe it actually comes underneath that. So this seems to be a consensus 4.493. Okay. Next step, because we're supposed to get, by the way, this is the x value, right? What do they really want to know? The question is, find the slope of that line correct to 6 decimal places. So what is the slope of that line?
4.493 over.
That's right. So we want the slope, which was, we had 2 different ways of finding the slope, didn't we? Negative cosine of x or negative sine of x over x. So when we want to check the slope where we are, let's just say we're going to go negative sine of 4.493 over 4.493, right? And that's like 0.2. Am I remembering the right values here? What's this negative sign of 4.493 divided by 4.493? I think I'm remembering that about 2/10.
Yeah. 0.217.
0.217. I think the final answer when you get it there is 0.20 something for the slope of this line. Slope of this line right here is about 2/10. And that's as large as you're going to get for the slope in this problem.
How do you know when, like, we got x2 is 4.493? How will
Right.
we know when we have?
You're going to have to do a couple more
Six
iterations.
decimal- Wasn't the question for 6 decimal places?
Yes.
And then
Yeah, it's going to get there very quickly.
can you plug it back into either the negative cosine or the negative sign?
That should work either way. Somebody check that out. What's negative cosine of 4.493? Same answer.
Okay.
Should work either way. So the next task, and then we'll finish, would be 4.493 minus the sine of 4.493
Why did we plug it in?
minus that value times the cosine 4.493 all over okay. So if you know how to program your calculator to do this iterative process, when you get to one like this, it starts to pay off for you.
Is there a thing in the book that tells you how to program your calculator? Because I've
They're probably online.
Okay.
And in fact, there may be something actually published by this textbook, the Stewart calculus text that tells you how to.
Or you could even just use the answer key, because if you have the answer and you just put second answer, it's just going to, instead of typing in 4.493, it's just going to take that decimal, put it back in.
Right, but remember, this is not your final answer. You want the slope at this. So you either want negative cosine of the value or negative sine of the value over that value. Okay, we'll wrap up anything we have to tomorrow with this and review for Friday's test tomorrow.